I'm Colin Walls, and I'm here once again to talk about embedded software. Today, I want to think about pointers. Now, pointers in C are a very useful feature of the language, possibly the most powerful feature in the language. But at the same time, they're probably the most dangerous feature of the language. They're the thing which is most easily got wrong. Now, if you've learnt C, you know what to do with pointers in general. But as soon as you get beyond the basics, there are possibilities for things going astray. Broadly speaking, actually, there's only one thing that can go wrong with a pointer, and that is it can be pointing in an unexpected way. It can be pointing to nowhere, so you have a null pointer, and that's actually quite easy to deal with because if you try to dereference the address 0, typically a processor will trap and you can do something about that. The real problem comes when a pointer points somewhere unexpectedly and gets some data or places some data in an invalid location. The problem with that is it will cause an error in the program at some point. So that point could be way after the location in the code where an assignment took place. The possibilities are endless in how this can occur. I want to go through a very simple example and show you how we can avoid this problem, as well as seeing the syntax and the semantics around pointers. Now, here is some code. In this code, we have a function fun, and inside that function, we have an array called ARR of 10 elements. It's an integer array. Presumably the function is going to do some processing on that array, and then at the end it returns the array. Well, actually what it does is, as you can see, the function fun is of type pointer to int. The name of an array, in this case AR, is a constant pointer to the storage for that array. So by returning just the name like that, we are not returning the array, we're returning a pointer to that storage. This is all syntactically correct, no problem at all. However, there is a problem with it, as we shall see. Now, we've got another function here, f2. In this function, I have got a pointer to int p. I've called function fun. I've assigned p to what fun returns. So p should now be pointing to the array ARR, or the storage of the array ARR. And I then say x equals p brackets 3, which means I'm going to place the fourth element of the array into the variable x. Unfortunately, that won't work. The reason it won't work is if we go back to look at the function fun, there's two things we learn from the code there. Firstly, the array ARR has a scope, which is limited to that function. So ARR as a symbol is not available outside of that function. That's not a problem, we're not trying to use it, so that's okay. But the storage of the array also has a lifetime which is bounded by that function. So the storage where that array is allocated has gone away. We don't know what it might be used for now. It's certainly not allocated on a permanent basis to this array. So when we assign the fourth element of that array into x, we wrote some data into x, but we don't know what that data really is. It could have been, that piece of memory could have been used for something completely different. So, how do we fix that? We fix it by a very simple change to the code. Now, this new version of the code has one tiny difference, and that is we have declared the array ARR as static. Now, what static means in this context, the keyword has several meanings, but in this context, what it says is allocate the storage for this array for all time. It's permanently allocated to the array, which means that when you return from the function fun, the array continues to be allocated to this purpose. ARR is still out of scope, but by returning a pointer, you're returning a pointer to valid memory. So when we do that assignment to x later on, everything's good. The downside of this, though, is that maybe having called fun, we don't really want that array anymore, but that memory is permanently locked up for this purpose. How do we fix that problem? Well, we can recode it like this. Instead of simply declaring an array, what we'll do is we'll declare a variable inside fun of type pointer to int called ARR. Just use the name again for consistency. Then I call the malloc function and allocate enough storage for 10 ints. I point ARR at that storage, do some stuff with it in the rest of that function. Then I return that pointer to the calling function. That's all fine, that'll all work. The allocation to malloc remains valid, so that when we are inside F2 and we call fun and then we assign the element of the array to X, everything is perfect. At some later point, when we definitely don't need to call fun anymore and therefore don't need the array AR, we just call the function free and deallocate that memory. So there's two different solutions to the initial problem. Both of them are valid. Both of them are absolutely fine use of pointers, so long as you think clearly about how a pointer is being used, where it's pointing at any given time. So I hope that clarifies some of the aspects of pointers. I'm sure pointers is a subject I'll return to in future videos, along with other subjects around embedded software. But that's it for today. So, bye for now.